Okay, everybody, let's get going on lecture 9, which is the last of our lectures immediately before the midterm on Thursday. So, midterm on Thursday. This is all stuff you've heard before. Make sure you arrive on time. You will probably need quite a lot of that time. Half multiple choice, half short answer questions in the same sort of style that you've seen in the discussion activities. So nothing spectacularly new. The seating chart will be available on Wednesday, tomorrow. I'll post it to the class website. You'll need pen and pencil. Please don't bring a calculator. You won't need to do complicated math. A Scantron form, the 288, the red ones, your student photo ID, and you're allowed an optional two-sided 3x5-inch note card of notes if you would like, okay? And you should be handing that in with the exam if you bring one. The study guide's on the website. It is just that, a study guide. It's just sort of a compilation of the lists of things that we've covered. You shouldn't just sort of memorize what's on there and hope that's good enough. Please do use your lecture notes and some of the reading as your primary sort of information. I'll reopen the quiz 4, so you can also take that for practice. And I'll also be in my office on Thursday from 10 to 12 for any last-minute questions. Does anyone have questions about the midterm? No? Yeah?
We asked us a question about relative humidity, for example.
Mm-hmm.
Would you provide us with the equation, or should we have
I will provide you with any equation that I would like you to use, so Wien's law, Stefan-Boltzmann law, relative humidity. Yeah, as long as you can use them, then that should be fine. I'm not bothered about you memorizing them. Anything else? Yeah?
Do you want our name on the note card?
Yes, if you could put your name on it, that would be great. Thank you. Yes?
It's double-sided, right?
Double-sided, yeah. Yeah. Sorry? We will have an online quiz as usual this weekend. It'll be nice and easy because there's only one lecture, right? So there's only so many things I can ask. So it's a good opportunity to claim some good points. Anything else? Okay. In that case, let us launch into some current events. Those of you that have been outside today, which is everyone here, know it's pretty hot. And it's really very dry. So I know that there was one discussion group that was out there measuring humidity before this class. What did you get? How much?
56%.
56? Today?
Today, no.
Oh, no. What was it today? 5? That sounds closer. Yeah, it feels really dry out there, right? So the Santa Ana winds have returned to us. And we'll cover them a little bit after the midterm, but since they're here, I thought it'd be nice to talk about them a little bit. So this is what our surface sea level pressure map looks like right now. So what have we got sat inland from us and to the north of us? Do we have a low or a high? Come on, guys. I know you can do this. It's only 2 days to the midterm. Low or a high? High. Thank you. Yes. So up inland from us and to the north, you can see that the numbers go up into the middle. So 24, 28, 32, 38. We have a high pressure. Is air going to be moving into or out of that high pressure? Out. And which way is it going to be spiraling in the northern hemisphere as it moves out? To the right. So it's going to be moving out and it's going to spiral that way. So we have this really dry air coming from over the continent, and it's coming down from the high desert. So those deserts are at a quite high altitude. And so as that air comes down and sinks down into the LA basin, what happens to it? Does it expand or compress? Compress. Does it cool down or warm up? Warm up. What happens to the saturation vapor pressure on my graph? Is that going to be high or low? It's going to be high, right? And we have very little actual. So our relative humidity right now is really low. We've got really hot air, but we have very little actual vapor pressure in there. So it's really quite dry right now. But more worryingly, we can deal with the heat and the dryness. That's really not a problem. But more worryingly, what's been happening over the other side of the US? Thunderstorms, tornadoes. So we have a big low pressure sitting over the other side. So if we have a quick look at our wind map, lots of videos today. So if we have a quick look at our wind map, you can see that that air is coming down from that high. It's coming offshore around here. That's what's making it windy and dry and hot. But we have this big low pressure that's been sat for a very long time over in this part of the world. And that has done some sort of very damaging things. So we have had a series of tornadoes. It killed, I think, 17 people over the last 2 days over on that part of the world. And you can see the devastation that these things cause as they move through. Those used to be houses, and they're just gone, okay? So we're going to come back to talk about thunderstorms and tornadoes after the midterm, but since it's happening, it's worth knowing about. And you can see that where these tornadoes and storms are happening, it's associated with this sort of area of really warm air coming up from sort of over this sort of marine area, and it brings lots of moist air, and then that collides with really cold air coming down in this way, so we get lots of instability. We have lots of clouds rising. Okay, so a quick review of what we did last week, because it always seems such a long time ago. So we talked about the different mechanisms that we have for lifting air. We know that as we lift air up, then it expands because the pressure gets less as we go up in the atmosphere. So how do we go about lifting that air? Well, first of all, if it bumps into a mountain, it has to go up and over, okay? So this is why we get, say, the Sierra Nevada mountains get more rainfall, more snowfall than elsewhere, and right on the other side, we have Death Valley, one of the driest places on Earth, and that's because we're in that rain shadow. It's coming down slope, so just like we have the Santa Ana winds being warmer and drier as they come down into the basin, so what's happening the other side of the Sierra Nevadas, and it would happen the other side of most mountain ranges. We have frontal lifting, where we have cold air moving in or warm air moving in, and one of those, that warm air, is deflected above the cold air, and as it rises, it cools down, it becomes saturated, and so we get clouds and rainfall. We have convergence, where we have air coming together. For example, in that low area, we have wind coming together. We're not going to keep piling that wind up forever. It's going to rise. And then lastly, we have localized convection. So one little part of the land surface might get a little bit warmer. The air above that surface might get a bit warmer than the surrounding air, and so we have this sort of convection going. And that can be at a relatively small scale. So within a sort of a few kilometers or so. These other ones tend to be much bigger scale, okay? And this is what's going on. If we look at maybe just that localized convection, this is what happens. We have air down here at the surface. As we lift that air up, it expands, it cools as it expands, and so we move towards saturation. Do you remember my saturation vapor pressure graph? Which way around is it? Yeah, this way around. We cool our temperature, we eventually hit that red line. We become saturated. And at that point, we start getting condensation. We're saturated, we're going to start seeing water droplets. And that process of water going from a gas to a liquid releases latent heat, that stored energy contained in those water vapor molecules. And that extra heat goes into heating the surrounding air. So now as that air continues to rise, it's still expanding, so it's still cooling down at 10 degrees per kilometer, but we have heat being added back in at 5 degrees per kilometer by this process of condensation. So that slows down the rate at which we cool as we go up, and that's our saturated adiabatic lapse rate. So hopefully this is sounding familiar. Okay, so everyone's favorite thing. So we had a go at this over the weekend, and I think most people got this. But I wanted to check. So our adiabatic lapse rates are really very consistent. What is our dry adiabatic lapse rate? 10 degrees Celsius per kilometer. What's our saturated one? 5. Always the same, okay? But our environmental lapse rate changes through time, changes in different places. So tell me, if my environmental lapse rate is 15 degrees Celsius per kilometer, what is my parcel of air going to be? So take a minute to think about it. Consult your neighbor. Okay, let's take a look and see if we agree. So we do agree. Well done, guys. You've clearly been studying, which is a good sign. So you are right. It would be absolutely unstable. Okay? So if we think about that environmental lapse rate, it's bigger than either our dry or our saturated lapse rate. So air in the environment, it would be cooler at any particular altitude than the air that's being forced to rise. And so that air that's being forced to rise is going to be warmer than the surrounding air, and so it's going to be less dense. Its molecules, we're going to have the same mass, but it's going to occupy more space, and so that will keep going up. It's going to be unstable. It's going to want to continue moving by itself, even if we take away that lifting mechanism. And it doesn't matter in this case whether it's saturated or dry. In both cases, that air would be warmer, continue to rise. Good work. So I wanted to give you another example for our inversion. So remember, we call an inversion, or an inversion is the term for extremely stable air. Air that really isn't going to go anywhere. And this is what results in our June gloom. So that other season that the California sees, we only really get summer and the June gloom. So what's happening here? Well, right now we have air moving offshore. It's coming from inland and it's moving offshore. But at other times of the year, we have air that sort of affects us here at the coast especially, that's been moving in across the sea. And the sea is really quite cold right now. And so it keeps that air close down to the ground really cold. And if we have a high pressure, we have air sinking from above, and that air warms up as it sinks. And so what we end up is with this layer of cool water, cool air down at the surface, and warmer air up above. And that basically keeps that cool air trapped down here at the surface. And so we get this sort of layer of low cloud, this sort of saturated air right down at the ground, and it's not going to be able to move up and away. Okay? So this is our inversion, which is fun. Then we talked about cloud types, and I said I didn't want you to memorize all of these different types, okay? But be aware that they are there, and that they have different effects on our climate system. And the last thing that we did was this. And no one liked my last iClicker question of the day. So let's have a look at my little feedback loops. So first of all, if I increase temperature, what do I do to the amount of water vapor in my atmosphere? Increase it. But that has two different effects. First of all, water vapor is a greenhouse gas, right? It's really good at absorbing outgoing infrared radiation. And so if we're trapping more of that outgoing radiation, what's going to happen to our global temperatures? They're going to increase again. So it's that sort of a positive feedback. We start with an increase and it leads to a further increase. But if we're increasing the water vapor in the atmosphere, what are we going to do to the amount of clouds? We're going to increase again. And what does that do to our albedo? It increases, we reflect more. We have this nice white fluffy clouds in our atmosphere. We're going to reflect more of that incoming solar radiation. What does that do to our temperatures? It decreases them. And so I asked you, well, what will increasing temperatures and having more water vapor in our atmosphere do to our temperature? And you all wanted to tell me one way or the other it was going to increase or decrease. And the answer is we're not entirely sure right now. We still would like to have a much better idea of what that is going to do. And it really depends on the type of cloud, where it forms, high up in the atmosphere or low down. And it's something that's really difficult for our climate models to get right. So we are still working on that. So, on to today. So let's think about precipitation. We know very, very well here in Southern California that just because we have clouds around doesn't necessarily mean that we're going to get rain or snow or hail or anything else. Okay? So why do some clouds cause precipitation and some don't? Well, it's because those little cloud droplets are really tiny. It's why they stay up in the air. It's why they don't all fall down as soon as they form. So if we look at my little diagram here, first of all, we have up in the clouds, we have what we call condensation nuclei, or this is one condensation nucleus. And they're really, really, really tiny. And these are our little aerosols, things like dust particles, bits of sea salt, sulfur, or even nitrogen oxides, things like that up in the atmosphere. And these provide a surface that water can condense onto. And so this is how big our little typical cloud droplet would be relative to our condensation nucleus. And after a while, we might get a much larger cloud droplet. But down here, right along the bottom, if you imagine how big that would be in comparison to these others, that's how big a typical raindrop would have to get before it will fall out of the cloud. Okay? So why does it matter how big they are? Why should we care? So let's think about forces. So precipitation is liquid water or ice that falls to Earth's surface. And so what's making it fall? What's keeping us on the ground? Gravity, okay? And the force of gravity is related to our mass. And our mass doesn't depend on our area or anything, it depends on our volume, okay? So if we're thinking about the mass of a little droplet up in the sky, then what we need to think about is its volume, which is going to be proportional to its radius cubed. Okay, remember volume is cubed. So that's the force that's pulling it downwards. That's what you feel when you jump out of a plane, okay, with a parachute. But has anyone parachute jumped? I think I've asked this before. One? Really? Skydiving, yeah. You don't keep accelerating all the way down, right? Okay? You hit what you call terminal velocity. And that's because after a while, you experience another force acting in the other direction. And that's drag. Okay? So as you're skydiving, or if you've seen pictures of someone skydiving, then they're feeling sort of force going the other way, right? Their sort of hair shoots up or their face ripples backwards and forwards. They're feeling this force going the other way. And that's drag. It's basically the resistance of those air molecules that you're bumping into as you're moving past them. Okay? And that drag is going to be related to the surface area. It doesn't care how heavy you are. All it cares is what sort of area you're presenting. So if you're skydiving, if you want to go fastest, do you spread out or do you go straight down head first? Straight down head first, right? Because you're trying to minimize your surface area, okay? And so that's the same thing. If you're a little droplet, then it's going to care about the surface area. And the surface area of my droplet is only going to be proportional to r squared, the radius squared. So as I increase my radius, what is going to get bigger more quickly? The mass or my surface area? So if I have a radius of 1, what will be my mass? Roughly 1 cubed, right? My area will be 1 squared, still 1. They're all 1. If I instead have a radius of 2, what would be my surface area? 4. What would be my mass? 8. So which is getting bigger more quickly? The mass, because it's r cubed. So as my little droplet gets bigger and bigger, the mass is increasing much, much more quickly than my surface area. And so the bigger the droplet gets, the more gravity it feels compared to drag. Does that make sense? Or have I lost everybody? No one's shaking their head, so I'll assume that we're okay. So terminal velocity is where that force due to gravity is equal to the drag. It doesn't mean that you stop. It just means that you stop accelerating. You stop getting faster. You just fall to Earth at the same speed. Okay? And so with increasing size, you're going to have an increasing terminal velocity. Okay? And so that droplet that we have up in the sky, it will fall down to Earth when its terminal velocity is greater than than whatever winds are moving it upwards. Okay? So we've all walked by on a misty day and we can see tiny droplets in the air and they're wafting around, okay? And that movement of air is keeping them in the air. And so we have the same things. If we have this movement of air upwards, generating our clouds, generating our condensation and everything else, then really for that drop to fall, it has to beat that updraft, okay? That upward moving wind. So, how do we get our cloud droplets to grow? So we saw how big that raindrop has to be compared to a cloud droplet. So how do we grow these sort of raindrops big enough that they will actually get large enough to fall out of the sky? So firstly, let's talk about warm clouds. So when I talk about warm clouds, I mean that clouds that are throughout their whole sort of mass, they are warmer than 0 degrees Celsius. Okay? And so they have water only. We don't have ice in there, we just have water. And so our droplets in this type of cloud grow by collision coalescence. They're all good words to try and spell. And the idea is that those different sized water droplets have different terminal velocities. So if you imagine my big droplet in my diagram there is falling faster than those small ones underneath it. And so it collides with them, and it will coalesce, it will join together with those to create a larger and larger and larger droplet, okay? And I know that this is an obvious one, but it is a video day, and so let's have a quick look. So you can see our little drops, and it's not always perfectly efficient. Sometimes they break apart again. But in general, they collide and they coalesce, okay? I also wanted to show this video because what shape is my little droplet as it falls? What shape do we draw raindrops on our page when we're kids? Teardrops, right? Does that look anything like a teardrop? No. They tend to be mushroom-shaped, if anything. Just a bit flattened out, okay? So a little bit different. So anyway, there's a whole 5 minutes if you particularly want to watch raindrops join together. Okay. So that one's a pretty easy one to deal with, I think. But now we come into cool clouds and cold clouds. So cold clouds, all the parts of that cloud are below 0 degrees Celsius. Cool clouds, part of them are below 0 degrees Celsius and part of them are above. And so these happen at mid to high latitudes. So the clouds above us will probably be cool clouds, okay? And these are a mixture of both liquid water, but also supercool water, which we'll talk about in a second, and also ice crystals. Okay, so let's talk about supercool water for a second. So, who's heard of this before? Anyone from my ESS 21 class, right? So, supercool water is something that is really fun, and very few people have heard of it. And the idea is that a lot of our water in the atmosphere is actually super cool. Water doesn't necessarily instantly become ice as soon as it hits 0 degrees Celsius in the atmosphere. And that's because often it doesn't have anything to sort of form ice crystals onto. So just like we had our condensation nucleus, where liquid water could condense onto it, for our ice to form, it also needs to have a nucleus to form onto. And the problem with ice is that it has this nice 6 sides to it. And so ideally, it wants its ice nucleus to be 6-sided, and there aren't that many of those floating around in our atmosphere. And so really, sort of below 0 degrees Celsius, anywhere sort of down to minus 40 degrees Celsius, our water can continue to exist as in a liquid form, even though it's much, much colder than 0 degrees Celsius. Below minus 40 degrees Celsius, it really doesn't care anymore whether it has something to sort of freeze onto or not. It will just spontaneously do it, okay? And because it is really good fun, I have a couple of videos to show you. So, for those of you that liked Frozen, this is a good thing for you. So what they've done here is they've taken a bubble solution and they've supercooled it, and they're going to drop little ice crystals onto it to allow that nucleation to happen. This isn't time-lapse. So these little ice crystals grow more or less instantly. So, you can also try this at home yourself. Oh, adverts. So it's liquid. More magic. So this is just a bottle of Fiji water or something that has really high purity. There's a lot of those bottled water companies. They filter the water, they take out a lot of the impurities in that water. And so if you put it in your freezer and leave it for maybe a couple of hours, then you can make super cool water. And you can get it out, and you can bang it onto a desk, and it lines up enough of those molecules that it will freeze instantly. So who from my ESS 21 class managed to do this for extra credit? 1, 2, 3, 4. Yeah, a few people. It worked, right? Took a few tries, but it was very, very fun. So you can have a go at that if you want as well. So there's one last little video there. Oh, go on, I'll show you. So this is the other really fun thing you can do with super cool water. If you get it really, really, really cold, and I've only had one student from my other class manage to do this, but it was still very, very, very fun. So there you go, a new magic trick to try. So we have this really fun substance in the clouds above our heads that we never knew about, this super cool water, okay? So let's have a think about how this super cool water interacts with ice crystals. So this, I think, is the most challenging bit of today. It's called the Bergeron process, and everyone in every class I've ever taught hates this stuff, okay? I have some notes for you. So I'm going to go through this twice. The first time, just listen to me, okay? And then I'll let you take some notes, and then I'll say it again and to see if we can get through this. So let's think about what's going on. Up in my cloud, I have a super cool droplet, okay? And it happens to be right next door, or right next to an ice crystal, okay? So here's my super cool droplet, here's my ice crystal. So ignoring the ice crystal for a second, just think about the super cool droplet. So here you can see that we have an equal evaporation rate to condensation rate. So this little droplet is going to stay the same size. And that's because, if you can just about see, there's lots of little, these represent water vapor molecules. So there are enough water vapor molecules surrounding this droplet that it's at saturation. We have equal amounts of evaporation and condensation, okay? So if this was all that's going on, that would be fine. But now let's introduce our little ice crystal. So if we bring this ice crystal and put it next to the super cool droplet, well, all of a sudden, for the same concentration, for the same number of water vapor molecules in the air, there's going to be much more deposition, that process where we go straight from gas to a solid, onto my ice crystal. Then we have sublimation, the return from that solid into a gas, okay? And that makes a certain amount of sense, because breaking a molecule free of that solid ice structure is going to take a lot of energy. It's going to be a very difficult process to do. So compared to our evaporation, this is going to be a much less fast process. So for the same concentration of water vapor molecules, we're saturated above my water droplet. but we're super saturated above my ice crystal. We're going to get more deposition than sublimation. Does that make sense so far? Yes? No? Maybe? So what happens is that that continues. We get much more deposition onto my little ice crystal compared to sublimation, and so my ice crystal grows. And in the process, it removes a whole bunch of these water vapor molecules from the air that surrounds my supercool droplet. And so now we're no longer saturated above my supercool droplet. Now we have less condensation because we have fewer molecules of water vapor compared to the amount of evaporation, which is staying the same. Okay? So what happens to our little droplet? It shrinks. Okay? We have less being returned by condensation than we have leaving due to evaporation. And so this process will continue until finally it's balanced again, until finally the rate of condensation is equal to the amount of evaporation. And then we've replenished the amount of water vapor molecules in the air. But look, my ice crystal's still there. It's still being greedy. It's still taking a lot more of those water vapor molecules and growing, and it's not returning many. And so eventually we go through this process until the supercool droplet evaporates away completely, and the ice crystal has grown much, much bigger. Okay? So we're growing our ice crystal at the expense of our little droplet. Okay. A lot to take in, right? So I'm going to give you a minute to quickly scribble some notes, and then I'll go through the process one more time. Okay? And I'll put up my notes as well if that helps. Okay, so one last time, just because I think this is complicated. So at the top, the air there is saturated above the water droplet. Okay, there are enough water vapor molecules that we have equal amounts of condensation water vapor molecules returning to that droplet as evaporation. So it's saturated. And if that was all that was in the atmosphere, that would be fine. Nothing would really change. But if we introduce an ice crystal next to that droplet, now it's super saturated above that ice crystal. For the same temperature, for the same number of water vapor molecules in the air, we're going to get much, much more deposition onto the ice crystal and less sublimation, less returning of those water molecules into the atmosphere. And so what that does is the ice crystal steals a whole bunch of those molecules and uses that to grow. But now that's a problem because we're no longer saturated above the droplet. We've taken a lot of those molecules away. So now we're going to have less condensation, less collisions of those water vapor molecules back with the surface. Instead, we're going to get more and more evaporation than condensation, and that's going to continue, and it's going to shrink my droplet. It's more leaving than arriving, until finally we have equal amounts of evaporation and condensation again. We're saturated again. But my ice crystal's still hanging out next to my supercool droplet. And so again, it's going to be super saturated now over that ice crystal again. And so it's going to steal more of those water vapor molecules from the air and deposit them and grow. And so what's happening is my supercool water droplet is getting smaller and smaller and smaller and smaller and smaller, and my ice crystal is getting bigger and bigger and bigger. Okay? So you can actually see this process in action too, in real time. Let me see. Here we are. So what they've done is they've just quickly sort of squirted an air duster, and that's provided enough energy to nucleate a few ice crystals. And that mist there is supercool droplets. Okay? But now you can start seeing through time, you can start seeing little sparkly ice crystals appear. And they're growing and they're getting bigger and bigger, and that's because that misty supercool droplets, they're evaporating, and that the water vapor is actually being added onto the ice crystal. Okay? So we're growing our little snowflakes through time. And I think this is really fun. I could watch this all day. Okay. So there we go, snowflakes growing, and that's the process that's happening in the clouds above us all the time. It's generating our raindrops. and we didn't necessarily think about all of this really crazy stuff going on up there. So we have two other processes where we can grow our ice crystals. We can grow particles big enough that they'll fall out of the sky. And that first one was by far the most complicated one. Our second and third are really easy. Okay? The second one is called riming, and all that happens is a nice big ice particle falls down, and as it falls down, because it's larger, it has a faster terminal velocity, it collides with lots of little supercool droplets. And so those supercool droplets instantly freeze when they come into contact with that ice particle. Basically, they just add on to that ice. And then lastly, we have aggregation. And this is, instead of having ice particles adding supercool droplets, now we have ice particles colliding with other ice particles, and in some cases they can stick together. That's our aggregation. And so they can grow just by joining together as well. Okay? So those two are a lot less complicated by comparison. So let's think back, see how carefully you were thinking and taking notes. So I have a cloud. The bottom part of my cloud is above 0 degrees Celsius. The middle part is about minus 20. And by the time I get up to sort of 7 kilometers high in my atmosphere, it's down to minus 40 degrees Celsius. So in which level of those clouds are we going to get ice, water, supercool droplets, things like that? So have a look, pick A, B, or C, and then we'll answer the question. So let's see if we have an agreement. We do? That's good, yes. So above 0 degrees Celsius, unsurprisingly, we have liquid water only. And below minus 40 degrees Celsius, then we really only have that ice. Even supercool water will start to freeze by itself at that point without necessarily needing something to sort of freeze onto. Okay, so let's think about our different types of precipitation. So the first one we're going to talk about is snow, partly because it's my favorite type and it's particularly beautiful. And these images here are actually photographs taken by a lab in Caltech just up the road, and they put a lot of work into growing these things and studying the process of growing snowflakes. So snow are basically just tiny crystals of frozen water vapor, and they grow by those different processes, Bergeron process, all of those others, by deposition of water vapor onto their surfaces. In order for us to get snow, if you've ever experienced snow, then the temperature from the cloud all the way down to the ground surface has to be below 0 degrees Celsius. If it goes above 0 degrees Celsius, anywhere between the cloud where these beautiful things are forming to the ground, then they're going to melt. Okay? So our first example is snow, and we really do need that temperature to stay below 0 degrees Celsius all the way down. So what have you heard about snowflakes? Why are each of them there different? So has anyone heard the myth that no two snowflakes are alike? Yes? So let's think about why that might be. Okay. So first of all, they have this amazing six-sided symmetry, right? Can't count it, 6 sides. And that's to do with that molecular structure of water again, that molecular structure of ice. You can see that we form these little hexagonal sort of structures within the ice crystal itself. And those are formed between the molecules themselves. So each of these little circles and things, this is a water molecule. And then we have these hydrogen bonds that form, and we get these hexagons. Okay? And so that's why we end up with our 6-sided snowflakes. But we get very different snowflakes depending on the temperature of the air and how supersaturated that air is relative to that ice crystal. So we might think of those sort of images as being our classic snowflakes, but actually we can get anything from sort of needle shapes down to just sort of simple hexagonal sort of plates into columns and other things like that. And there's loads and loads of photos taken from this Caltech website if you want to go and have a look at more. So tell me, what sort of snowflakes would form if the temperature is minus 20 degrees Celsius and I have a supersaturation of 0.25 grams per meter cubed. So what sort of snowflake would I get with those conditions? Yeah. So we would get dendrites. So if we look along the scale, make sure you're looking at the right temperature scale. If we have minus 20 degrees Celsius, if we go up to say 0.25, then we get dendrites. Okay? So who in here is a snowboarder? One? I'm sure there's more than you, but no one else is admitting it. Okay, so what you tend to like is powder snow, right? So you want powder. That tends to be formed at really cold temperatures, okay? If you want to throw a snowball at someone, then actually you want the sort of snow that sticks together nice and easily, and that's sort of more what we get at 0 degrees Celsius or so, okay? And so when we get snowfall, those different shapes will occur at different times, right? Because our snowflake isn't going to stay stationary in the atmosphere, forming at that one particular temperature, at that one particular degree of supersaturation. It's going to be moving constantly throughout the cloud, and it's going to encounter different conditions as it falls to Earth. And so that's why we say that each snowflake is unique. It doesn't necessarily need to be the case at all. But what we see is that each snowflake has such a unique path through the cloud that they all form their own little shapes as they go, and they sort of switch between these different forms. So they might be dendrites for one part, but then they might get more needly, okay? So that's why we see such a huge diversity in our snowflakes, which is really fun. So, rain. This is something that we're more familiar with, and I got completely soaked through on Friday trying to cycle home. I'm sure someone else did as well. So if you are in the tropics, what is forming your raindrops is really that collision coalescence process. That's what's happening in those warm clouds above you. But right here, we know that we get rain as well. And that's because even though actually in the clouds above us, we have this Bergeron process happening instead, we have rhyming, we have aggregation. Well, yes, that's fine because it's really cold up there, but by the time those sort of ice particles get down to us, they've encountered much warmer air and they've melted. So we really see those as raindrops instead, which is a shame. So that's our rain. Graupel, it's a funny word. Graupel is basically a bit like hail, but it's soft. You can sort of squeeze them together. And it's because there's lots of air in there. There's sort of air pockets. So this is sort of graupel on the right-hand side here. And who's experienced hail? Most people, right? Hopefully most people. How big was the hail that you experienced? So that guy experienced really big hail. Listen. So often they're that size, right? It hurts though, right? When you're outside and it hits you, it's pretty sore. So hail is a really fun thing because we even get that here where it's actually pretty warm, okay? And that's because even though the temperatures below the cloud may be above 0 degrees Celsius, it's actually quite a large, frozen, solid piece of ice. And so it takes a while to melt as it sort of falls. And so often when it reaches us at the ground, it's still frozen. And when do you tend to get hail around here? When do you tend to get hail? Thunderstorms, absolutely. And so what's happening here? So if we have hail, they're actually pretty heavy, right? What does that mean about how strong the updrafts are? So remember that our piece of ice, our droplet, will fall to ground once its terminal velocity is bigger than the speed of the updrafts, okay? So how big do you think the terminal velocity is of a hailstone? Pretty big. They fall quite fast. So how strong would the updrafts have to be to keep them in the air? Pretty strong. And you can get big hail as well, okay? You can get big hail. So I'm going to show you an example of big hail. So this one I will turn the sound on, and you can ignore the guy because he's really not saying anything helpful. But he is sort of making the point that it's pretty loud. you can get quite big hail. So how big do you think the updrafts must be to keep those hailstones in the sky? Really intense. So what do you often see associated with hailstorms like that? Tornadoes, okay? So these are the sort of hailstones you get in really, really severe thunderstorms. Because really, to build something that big takes a huge amount of upwards moving air, okay? And that really strong updraft is really what a tornado is. If we can get some rotation going, then that sort of is what our tornado is a really strong rotating updraft, okay? So we'll talk much more about that after the midterm, but really remember that hail can get big. So, sleet. This one is less exciting. The idea is that we again have these ice particles forming in this cool, cold clouds above us. And then once they start falling to ground, they actually encounter nice warm air. And so they melt and they start forming raindrops. But, for example, if we have an inversion like we have during the June gloom or something like that, where we have a really cold layer of air close to the ground, then actually if that air is underneath 0 degrees Celsius, then that raindrop can actually start to refreeze again. And it doesn't form beautiful ice crystals or the beautiful snowflakes that we see forming in clouds, but they do form these sort of ice pellets that are pretty miserable. Okay? So that's sleet. And then the last one we have is freezing rain. Has anyone ever encountered freezing rain? One person. It's fun, right? I'll post a stupid video. You would disagree. I don't know. I only encountered it once or twice when I was a kid, and it was really fun because you can't move anywhere. Basically what happens is that we get these super cool droplets, and they drop to the ground, and they freeze more or less instantly. They might form a thin film of water which basically instantly freezes. And this is the sort of thing that you get as a result of this. So that is someone's car, although it's going to take him a while to get into it. You can also see the damage that it does to trees and to power lines, because that water will basically stick to everything, okay? And it makes it really slidey. I'll post a stupid video to the the Facebook page of someone trying to park their car up a slope after freezing rain. It just doesn't work. You can't go uphill, because there's nothing to hold on to. Everything is coated in ice. So you can try sort of edging your way uphill and you just end up sliding straight back down again. So it's fun as long as you don't have to go anywhere. But this is incredibly damaging. So up in Canada, if you've heard of the ice storms that hit up in Canada and northern parts of the US, this can take power out very easily. So you can see what happens to the power lines there. And also tree branches get so heavy and they break, and they sort of break those power lines as well. And so it's very, very difficult to deal with, and so you often end up sort of out of power for hundreds of thousands of people in the middle of a very, very cold winter, and you don't necessarily want that. So this is sort of what that temperature profile would look like. So on the left of my little scale at the bottom, I have colder than 0 degrees Celsius, okay? And then on the right-hand side of that little X scale, I have warmer than 0 degrees Celsius. So you can see that up in my cloud, it may have been cold, it may have been under freezing, and we formed nice snowflakes and supercool droplets. And again, those then fall through a nice warm layer of air, and they melt and form raindrops. And then if we fall through a really, really cold but thin layer right next to the ground, then they don't have time, those drops don't have time to refreeze, but they do have time to get cold, okay? So that's the difference between sleet and this freezing rain. The sleet has sort of a thicker amount of cold air to fall through, and so it can refreeze, whereas this stuff doesn't. So, having a look at my lovely temperature profiles. So again, on the left of the x-axis, we have below 0. My line going vertically is 0 degrees Celsius. And then on the right-hand side, the temperature is warmer than 0 degrees Celsius. So which temperature profile do you think is typical for the formation of sleet? And then see if you can work out what the other two are showing you. Okay? So So let's see if everyone can read my diagrams. %70 of people can read my diagrams. So for those of you that picked C, what does it say is reaching the ground? Snow. So it'd be snow, right? And why else would there be snow here if it didn't say snow reaches the ground? How would you know that it was snowing? Apart from that it looks like snowflakes. What is my temperature like? It's always below 0 degrees Celsius, right? So it's going to stay as nice snowflakes all the way from the cloud to the ground. So here we have our little supercool droplets. What happens when those supercool droplets hit the ground? They freeze. So what did we call that? Freezing rain. Okay, so there's a much narrower layer of cold air. Those little droplets don't have time to form ice again, but they can become supercool. And when they hit the ground, they freeze. That's freezing rain. And so A is where we have this thicker layer of cold air, and those drops start to refreeze. We get ice pellets instead. So my A is my sleet in this example. So what would my temperature profile look like? What would my red line look like if I wanted you to show me what rain from a warm cloud looked like? Where would you draw the red line? Yeah, I draw it on the right-hand side of my diagram, right? So just like snow shows my temperature profile being always to the left, the cold side of 0 degrees Celsius. If I wanted to show rainfall from a warm cloud, remember warm clouds are above 0 degrees Celsius, and rain is going to be above 0 degrees Celsius, so it would probably stay more or less on this side. Okay? So hopefully that makes sense. So how do we go about measuring precipitation? How do we go about sort of working out how much of anything we have? Well, first of all, we have rain gauges, and that's a really nice, easy one, right? So we just have a pillar or a funnel, and it collects rain. But what might be a problem? What might cause us not to get perfectly accurate measurements from a rain gauge, from just a funnel that's collecting rain? Yeah? Sorry? Hail?
No, like dew, like ice.
Oh, yeah, absolutely. So yeah, you might get condensation or something else going on in there. It might change your values. What else often happens? What was it like on Friday when it was raining? Did the rain come straight down? No, what happened? We had wind as well, right? So there's turbulence above that sort of funnel. We're not necessarily going to collect all of the rain that might fall. We also see really patchy bits of rain, and we know that if we speak to friends, right, when the storm comes through. So it's raining here, and over there it might be fine, okay? Why can't we use rain gauges to measure how much snow we have? Because we care quite a lot about measuring how much snow we have, because we get a lot of our water supplies from snow up in the mountains of the Sierra Nevadas. So we really care about how much water's up there. No one's encountered snow enough. We have different density of snow, right? We might be saying we have a meter of snow, but depending on the type of snowflakes, and other things like that, and how compacted it is, we could get varying amounts of water from that snow. And so it's actually much more difficult to measure just the height of our snow and get a realistic sense of how much water there is contained in that. And so we use something else. We use that middle diagram there. We use basically like a big air mattress. And that air mattress is filled with an antifreeze liquid. And what will happen as I keep piling sort of snow on top of that liquid is that some of it will be forced out and up sort of a column at the side, okay? So what happens is that this little pillow is sort of laid out on the ground, and it's filled with an antifreeze liquid, and as that sort of snow builds up on top of these sort of pillows of this air mattress type thing, then antifreeze liquid is pushed out and pushed up this column. Okay? And then we can read off and see how much we have. So hopefully everyone has heard of Doppler radar, right? Maybe. So there are lots of Doppler radar stations set out across the US. And what they do is that every sort of now and again, they send out a pulse of radio waves, of microwaves. So they have a wavelength of a few centimeters or so. And so they'll send out a pulse in all directions. And what happens is that then they sort of pause for a while. And if that pulse, that wave bumps into anything like a raindrop or a snowflake or something like that, or cloud droplets, then some of that outgoing pulse will be bounced back to the tower. And how much is bounced back to the tower will basically tell you how much water, how much how many particles are in the air. Okay? So let's take a look at our current Doppler radar. So what do you think we will see around us? Not a lot. So we can zoom in a bit over us. And unsurprisingly, I'm not quite sure what this is. Maybe low cloud. But it's not very exciting. Okay? Where might we see something a little bit more significant right now? Over here. So let's zoom in and see how they're doing on the East Coast. Okay? So now you can see that we see all of these colors. And the paler blues are not as much reflected back, so there's less intense rainfall. And the brighter colors are really intense rainfall. And you can see that there are these little outlines here, like there's a red outline there. That is actually telling you that there's a tornado warning actually right now over in this area. And it's associated with this thunderstorm, which is giving really strong reflections back to the Doppler radar tower. Okay? So that's something that the US is always doing, and you can see all of the different radar towers here, and you can click on one, and it will show you the rainfall that's happening in any of these places at any one time. So there you go. And then the last way, which is sort of something that we can do now with satellites, is we can actually measure the amount of latent heat that is released at different altitudes in our atmosphere due to the condensation process, which is really very neat. And so what we tend to get are things like the diagrams on the right-hand side there. And those are really helpful for telling us what's happening throughout the atmosphere. So that's very cool as well. So, cloud seeding. Has anyone heard of this before? A few people? So one of the reasons it hasn't really caught on is because it doesn't seem to be hugely effective. We can't seem to do it very well. So the idea is that if there aren't very many condensation nuclei up in the clouds, then it's difficult for our ice crystals to form. It's difficult for our droplets to condense onto things. And so it's difficult to create precipitation. And so one of these ideas is that, well, maybe if we took a plane and we flew through this really moist air and released a whole bunch of ice nucleation particles, bits of dry ice or silver iodine, which is nice and six-sided, then maybe we could start this process and we could actually generate rainfall in an area that we wanted to a little bit downwind. Okay? And this is a really nice idea. The problem is it just doesn't work terribly well. Okay? And so there are other issues. Why might there be legal issues with cloud seeding? Why might someone have a problem with you going up and dumping cloud particles or nucleation particles in an area? Sorry, say that again? Farmers. Why would they be pissed? Maybe, so it would certainly change the local weather. So your local farmers might like you, perhaps if there's a drought. But what about further downwind? Because there's only so much moisture, right? If it rains in one place, it means it's not going to be raining somewhere else. So it's a bit like how much right do you have to take all the water from a river and leave none for further downstream? So if you're changing where it's raining, if you're changing where that precipitation is forming, then you have a problem if you're further downstream. Okay, so definitely there are issues with that. Okay, but we still have this nice idea because we come back to this idea, if you remember our feedback loops that we looked at the very beginning of class. Okay, and people have proposed relatively seriously little gadgets like this that sail around on top of the ocean and pump sea salt and things like that up into the atmosphere with the purpose of putting condensation nuclei, putting water vapor into the atmosphere to create clouds. Why do you think people are doing this, suggesting this? Why would extra clouds over the ocean be a good thing potentially in our future? Yeah, absolutely. If we have an increased albedo due to more cloud cover, then we might cool down our planet a bit, okay? And so people are proposing somewhat crazy ideas like this, okay? So, I have a challenge for you. So we didn't have as much to do today, and so I thought I would help you study and give you a little extra credit opportunity at the same time. So, either by yourself or in groups of 2 or 3, why don't you have a go at writing a multiple choice question? If you don't do this as a way of studying, you should do it. It's a really good way of thinking critically about the material instead of just trying to memorize it. Think, what could I ask you? So can you write a question that you think 75% of people roughly would get right? If it's a good question, I'll use it. You'll see it on Thursday, you'll get it right, and I'll give you an extra credit point as well, okay? So write it down, put your names on the top, and hand it to your TAs. And after that, you're very welcome to go.